Every year, nuclear submarines carry crews of over 100 people thousands of meters below the ocean surface, staying submerged for months at a time without surfacing. But how does a vessel weighing thousands of tons actually sink, hover at a precise depth, and rise back to the surface on command? The answer lies in three elegant engineering principles working together. The fundamental principle behind submarine diving is deliberately controlled buoyancy. Every submarine contains large tanks called ballast tanks, positioned between the inner pressure hull and outer hull. When the submarine is on the surface, these tanks are filled with air, making the vessel buoyant enough to float. To dive, valves at the top of each ballast tank open, allowing air to escape while seawater floods in through openings at the bottom. As water replaces air, the submarine's overall density increases beyond that of surrounding seawater, and it sinks. To surface, high-pressure air stored in onboard cylinders is blasted into the ballast tanks, forcing the seawater back out through the bottom openings. As water is expelled and replaced with air, the submarine becomes less dense than surrounding water and rises. This process is called blowing ballast and can bring a submarine from depth to surface rapidly in emergency situations. Controlling depth precisely while submerged requires a more refined system. Submarines use smaller tanks called trim tanks and compensation tanks to make fine adjustments to buoyancy. As crew members move around, food is consumed, torpedoes are fired, or equipment is used. The submarine's weight distribution changes constantly. The trim system continuously adjusts water between tanks to maintain perfect balance and depth. Physical depth control also relies on hydroplanes, movable fins positioned at the bow and stern of the submarine, functioning similarly to aircraft control surfaces. By angling these hydroplanes, the submarine can be driven upward or downward through the water while moving forward, allowing precise depth control without constantly adjusting ballast. Nuclear submarines solve the underwater endurance problem through onboard nuclear reactors that generate essentially unlimited power for propulsion and all ship systems. This reactor heats water to produce steam that drives turbines connected to the propeller shaft. The same steam system generates all electrical power aboard. A nuclear submarine theoretically never needs to surface for fuel. It can remain submerged for months, limited only by food supplies for the crew. Crew survival underwater requires completely self-contained life support. Oxygen is generated by electrolysis, splitting seawater molecules into hydrogen and oxygen using electrical power. Carbon dioxide exhaled by the crew is absorbed by chemical scrubbers containing lithium hydroxide. Fresh water is produced by distilling seawater. The submarine is essentially a sealed artificial environment capable of sustaining human life indefinitely. Pressure at depth presents an extraordinary engineering challenge. At 400 meters, depth water pressure reaches approximately 40 atmospheres, 40 times surface pressure. Submarine pressure hulls are fabricated from high-yield steel or titanium alloys up to 50 millimeters thick, carefully shaped into cylindrical and spherical forms that distribute compressive stress evenly across the entire structure. Modern military submarines operate at classified maximum depths, but are generally engineered to withstand pressures significantly beyond their operational limits, providing critical safety margins. The deepest diving military submarines are believed to operate below 600 meters, with safety factors built into their hull designs. If this explanation helped you understand something new today, hit the like button. It helps this channel reach more curious minds like you.